Okay. So, this is our IFD is equal to this expression, right. Now, this RAIQ is the voltage drop and omega r LD ID, right. So, this we omega r LD ID. So, generally L omega is reactance. So, this term we can make XD ID, right. So, that is why this IFD, this term equation can be written as EQ plus RAIQ plus XD ID and omega r LAD, L omega generally reactance. So, omega r LAD. So, this is XAD, this is equation 147, right. Now, the inductances or reactances appearing in equation 137 to 147, they are basically we are using saturated values, right. So, next is the phasor representation. For balanced steady state operation, the stator phase voltages may be written as, right, that is EA is equal to EM cos omega ST plus alpha, right. And similarly, EB is equal to we can write EM cos omega ST minus 2 pi by 3 plus alpha 120 degree phase shift. Similarly, EC is equal to EM cos omega ST plus 2 pi by 3 plus alpha, this is equation 150, right. Now, where omega s is the angular frequency and alpha is the phase angle of EA with respect to the time origin. Now, applying the dq transformation for this thing, earlier we have seen dq transformation. If you apply the dq transformation, it will give ED will give EM cos omega st plus alpha minus theta, this is equation 151, and EQ will give EM sin omega st plus alpha minus theta, this is equation 152, right. Therefore, now the angle theta we have seen, there is figure 9 we have seen. The angle theta by which the d-axis lead the axis of phase A is given by, you can write theta is equal to omega r t plus theta 0. This is equation 153 and theta 0 is the value of theta at t is equal to 0, right. Now, with omega r equal to omega s, right, because it is running, machine is running at synchronous speed, say at synchronous speed, substitution for theta in equation 151 and 152, it will give you ED is equal to EM cos alpha minus theta 0. That means, your this thing, your this one, your here, this only we are writing say only one term, say this is omega st plus alpha and minus theta is equal to omega r t plus your theta 0, right. So, this one actually omega st plus alpha minus omega r t minus theta 0, but omega r is equal to omega s, right. Therefore, this term will be cancelled. So, ultimately it will be say alpha minus this one, this term will be alpha minus theta 0, right. So, that is why here we are writing that ED is equal to EM cos alpha minus theta 0, this is equation 154, and EQ is equal to EM sin alpha minus theta 0, that is equation 155, right. So, in the above equation, that is EM is the peak value of phase voltage, right, and in steady state analysis we are interested in RMS values and phase displacement rather than instantaneous or peak values. Now, using ET to denote per unit RMS values of armature terminal voltage and noting that per unit RMS and peak values are equal, because when we converting it to the per unit values, RMS value and peak value they will be equal. Therefore, we can write like this, ED is equal to ET cosine alpha minus theta 0, this is equation 156, and EQ will be ET sin alpha minus theta 0, this is equation 157, right. Now, okay, just hold on. Now, the dq components of armature voltage are scalar quantities, this we have seen before. However, in view of the trigonometric relationship between them, they can be expressed as phasors in a complex plane having d and q axis as coordinates, right. For example, this is my your what you call, this is my q axis, this is my q axis and this is my d axis. So, Et tilde is the phasor quantity, that is right, and this angle is delta I, and this angle your alpha minus your what you call theta 0, because ED is equal to ET cosine alpha minus theta 0 and EQ is equal to ET your what you call sine alpha minus theta 0 and this angle is delta I. Similarly, here also Qx is I have not written here, this angle actually delta I, right. So, similarly, if you and this is say ET tilde, right, and this IT is the current. Therefore, ET is lagging from your IT tilde is lagging from ET tilde by an angle phi, right. So, in this case, for this case your what you call that ED is equal to your in general ET cos alpha minus theta 0, whatever we have seen before. Similarly, EQ is equal to ET your sine alpha minus theta 0 this side, right, but this angle delta I will come later, right, and this angle is delta I. Similarly, for the current, right, and this angle I told you this angle is delta I. So, similarly, for if you just see this is my this is delta I and this is phi, right. So, this angle actually 90 degree minus delta I plus phi, right. Therefore, ID will be is equal to IT cos 90 degree minus delta I plus phi, that is ID is equal to IT sin delta I plus phi. Similarly, IQ will be your IT cos delta I plus phi, right. So, so this is voltage component and this is current components, right. And this is figure something mark 15 representation of DQ components of armature voltage and current as phasor. Now, the armature terminal voltage may be now it can be written in complex form that ET tilde will be ED plus JEQ. This is equation 158 because here you have this ED, this is EQ. So, ET we can write as ED plus JEQ. So, we are writing ED plus JEQ, this is 158. Now, by denoting delta I as the angle by which the q axis lead the phasor ET, right, equation 156 and 157 it become that ED is equal to ET sin delta I and EQ is equal to ET cos delta I. Now, if you look into this, then your once again that if you look into this, your EQ will be is equal to ET cos delta I if you take delta I, and similarly ED will be is equal to ET your sin delta I, right. So, that is what we are writing here. So, similarly, for ID I told you, similarly the DQ component of the armature terminal current IT can be expressed as phasor. If phi is the power factor angle, we can write ID is equal to IT sin delta. This I told you that this angle, it is not marked here, but this angle same thing between Q axis and ET. So, this angle is delta I, right, and therefore, this angle is 90 degree minus delta I plus phi. Therefore, here I am writing, therefore, ID is equal to your IT, then this one will be cos 90 degree minus delta I plus phi, right. So, that is nothing but your IT, it will be sin delta I plus phi, right, that is ID. Similarly, IQ will be is equal to IT cos delta I plus phi. So, that is what it has been written here, right. So, this is ID is equal to IT sin delta I plus phi and IQ is equal to IT cos delta I plus phi. This is equation 161 and this is 162. Now, and IT tilde is ID plus JIQ. This is equation 163 because it is complex now, right. So, in this way you can represent IT is equal to IT tilde the phasor ID plus JIQ, this way you can represent. From the above analysis, it is clear that in phasor form, right, that is in your what you call in the phasor form with DQ axis as reference, the RMS armature phase current and voltage can be treated the same way as is done with phasor representation of alternating voltage and current. So, this way you can make it the way we represent the phasor quantities in in that your what you call in AC. This provides the link between the steady state values of DQ components of armature quantities and the phasor representation used in conventional AC circuit analysis, right. So, this actually DQ your conventional AC circuit analysis and in the DQ component, this actually there is a link, right. This actually provides the link. So, that means the relationship between DQ components of armature terminal voltage and currents are defined by your this equation 137, 138, 140 and 141. That means, my ED can be written as minus omega r psi q minus RAID, right. Similarly, your or psi q, we know from psi q is equal to LQ IQ. So, we can write omega r, that is your psi q is equal to LQ IQ, that has been substituted here. So, omega r LQ IQ minus RAID, and omega r LQ actually is nothing but XQ. So, XQ actually XQ is equal to omega r LQ. So, basically ED is actually XQ IQ minus RAID, right. So, this is actually equation 164, right. Similarly, your EQ is equal to omega r psi d, right. So, omega r psi d minus RAIQ. Now, from the psi d expression, if you substitute here, you will get EQ is equal to your minus XDID, then plus XAD IFD minus RAIQ. You put that previously we have derived the psi d expression, just you put it here and you will get this one, and this is my equation, this is our equation 165, right. Now, the reactances XD and XQ are called the direct and quadrature axis synchronous reactances respectively. So, XD is the direct axis and XQ is the quadrature axis synchronous reactances, right. Little bit exercise you do, just put this psi d expression previously derived and you will get this one. Now, they represent the inductive effects, right. They represent the inductive effects of the armature MMF wave by separately you are accounting for its D and Q axis components, right. Now, this is what is XD and XQ. Now, we have not yet developed a means of identifying the D and Q axis positions relative to ET tilde, right. In order to assist us in this regard, let us define a voltage EQ tilde, that means we are defining a voltage say EQ tilde, right. So, that means we are defining say EQ tilde is equal to ET tilde plus RA plus JXQ into IT tilde, this way we are defining say. Now, ET is equal to ET tilde is equal to ED plus JEQ, therefore, EQ tilde is equal to ED plus JEQ plus RA plus JXQ into ID plus JIQ. This is equation 166, right. So, now substituting equation 164 and 165 followed by reduction of the, you just hold on, followed by the reduction of the resulting expression, it gives actually following expression for EQ tilde in phasor form with D Q axis as reference, right. Therefore, in equations 164 and 165 you substitute, right, equation of 164 and 165, that means this one, that means this one, that is your equation 164 ED expression and EQ expression, and then you simplify, you substitute and you simplify. If you simplify, right, then you will get EQ tilde will be J into XAD, capital XAD IFD minus in bracket XD minus XQ into ID. This is equation 167. That means, it is a pure complex quantity is coming, that this EQ tilde will lie on the Q axis, right. Therefore, the corresponding phasor diagram is shown in figure 16. So, this is EQ tilde because it will lie on the Q axis, because only J, no real part is involved, right. So, it is J. So, this is EQ tilde is equal to ET plus RAIT plus JXQ IT, right. So, whatever we have assumed here, EQ tilde is equal to ET tilde plus RA plus JXQ IT tilde. So, this is the phasor diagram, and IT is lagging from ET by an angle phi not shown here. This is ET and this is IT, this is D axis and this is Q axis, right. Therefore, the corresponding phasor diagram is shown in figure 16, this is figure 16, right. So, we see that the phasor EQ tilde lies along the q axis. The position of the q axis with respect to ET tilde can be identified by computing EQ tilde, the voltage behind that is R A plus J X Q, right. So, that means your this one R A plus J X Q, right. Next is rotor angle. Under no load or open circuit conditions, ID is equal to IQ is equal to 0, right. Therefore, substituting equation 137, 138, 140 and 141, this it will give, because under no load or open circuit condition, ID and IQ both are 0, you substitute that in those equation, in equation your 137, 138, 140 and 140, you substitute that. If you do so, psi d will be equal to LAD into IFD, psi q will be 0, ED will be 0 and EQ will be XAD IFD, right. This you will get. Therefore, ET tilde we know ED plus JEQ, but ED is equal to 0, therefore, ET tilde will become JXAD into IFD. This is equation 168, right. So, under no load conditions, ET tilde has only the q axis component and hence delta is 0, right. So, just hold on, right. As the machine is loaded, delta I increases. Therefore, the angle delta is referred to as the internal rotor angle or load angle of the machine, that you have studied in synchronous machine, right. So, as the machine is loaded, delta I increases. Therefore, the angle delta is referred to as the internal rotor angle or load angle of the machine. The relationship between power output and the rotor angles is non-linear and is of fundamental importance in power system stability studies, right. The angle delta I actually represents the angle by which the q axis leads the stator terminal voltage phasor ET tilde, and it is given by that I told you earlier that delta I will be 90 degree minus alpha minus your theta 0, right. So, this is actually your what you call that your delta I. So, if you go back to that previous figure 15, you see the delta is equal to 90 degree minus alpha minus theta 0. This is equation 169, right. Now, where alpha is the phase angle of EA and theta 0 I told you before is the value of theta with respect to the time origin, say at t is equal to 0, right. Therefore, delta I depends on the angle between the stator and rotor magnetic fields, right. For any given machine power output, either alpha or theta 0 may be arbitrarily chosen, but not both. You have to choose either alpha or theta 0 for any given power output, but not both, right. So, that is the condition. Now, steady state equation, a steady state equivalent circuit. If saliency is neglected, then we can assume x d is equal to x q is equal to x s, right. If we neglect the saliency, then x d is equal to x q is equal to x s, right, where x s is the synchronous reactance. We are assuming both are same. Therefore, we can write E q tilde we know E t tilde plus R a plus j, it was x q. So, now x q is equal to x s. So, j x s into I t tilde, this is equation 170, right, where x d is equal to x q. So, from equation 167, the magnitude of E q is given by. So, this is then E q will be x a d I f d. So, that is from equation 167, I mean here. This is your E q is equal to x a d I f d, right. This is your just hold on 167, right, because x d is equal to x q, here x d is equal to x q. So, is equal to x s. So, x d this term will not be there. So, it will be only j into x a d I f d, but if you take the magnitude, then E q will be only is equal to x a d into I f d, only magnitude. So, that means your this is my capital E q is equal to x a d into I f d, this is equation 171, right. Therefore, resistance Ra is usually very small and may be neglected. Therefore, this equivalent circuit we can make that this is my EQ angle delta I, this is Ra excess and this is Et 0. Only one thing I have to make it that this is the current, this is say It tilde, right. Therefore, EQ is equal to x AD IFD magnitude 1 and xd is equal to xq and xs. This is Et angle 0 and this is we have taken EQ angle delta I. That means, if you take this one as a reference, so EQ leading Et by an angle delta I, because this was your q axis and this is your EQ and this was your Et and this angle was your delta I, right. So, basically EQ leading Et by an angle delta I, if Et as a reference, so Et angle 0, right. That is why we have written Et angle 0 and EQ angle delta I and Ra excess, right. If you want to put J, you can put J here, right. But generally for machine Ra is very small, can be neglected, but this is the equivalent steady state equivalent circuit, right. So, the voltage EQ may be considered as the effective internal voltage, right. So, the voltage EQ may be considered as the effective internal voltage, right. It is equal in magnitude to XAD IFD that we have seen just now and hence represent the excitation voltage due to the field current, because it is XAD into IFD, IFD is the field current, right. The synchronous reactance XS accounts for the flux produced by the stator currents, that is the effect of armature reaction, right. For a round rotor machine, right, xd approximately is equal to xq is equal to xs we have taken. Therefore, the above equivalent circuit provides a satisfactory representation, right. For salient pole machine, of course, xd not is equal to xq. The effect of salience is however not very significant, right, so far as the relationship between terminal voltage, armature current, power and excitation over the normal operating range are concerned, right. The approximate equivalent your what you call often provides sufficient insight into the steady state characteristics. Only at small excitations will the will the effect of saliency become significant. The approximation also regards the reluctant your what you call neglects the your reluctant torques due to saliency, right. Now, next is active and reactive power. Now, we know S is equal, we know in general from load flow studies, we know that either when you write in general we write that P minus Jq is equal to V conjugate I or P plus Jq is equal to Vi conjugate, right. So, similarly, active and reactive power we write S the apparent power Et tilde It tilde conjugate. So, Et tilde is equal to Ed plus Jeq and It is conjugate, It is equal tilde is equal to Ed plus Jiq. So, It tilde conjugate is Ed minus Jiq, that is Ed minus Jiq, right, sorry Id minus Jiq. So, Ed plus Jiq into Id minus Jiq. Therefore, and S is equal to your S is actually Pt plus Jqt because it is Ei conjugate, right. Therefore, Et you can if you multiply it, it will be Ed plus Eq plus J Eq minus Ed. Now, you separate real and imaginary part. So, Pt will be Ed plus Eq and Q2 will be Eq minus Ed. This is equation 172, this is equation 173, right. Now, steady state torque is given by T is equal to this we have derived that psi d Iq minus psi q Id, this we have derived, or simply this one if you just put those psi d psi q all this expression you will get T is equal to this one little bit I ask you to derive of your own, right. So, just put those expression you will get T is equal to Ed plus Eq plus Ra into Id square plus Iq square, or T is equal to this is my power, just now we have seen Ed plus Eq this is my power Pt, right, just now we have seen, and this is Ra It square because your It tilde is equal to E or sorry just hold on It tilde is equal to Id plus Jiq therefore, your magnitude, if I take magnitude of this one is equal to this one, right. Therefore, my I t square is equal to your I d square plus I q square, right. That is what is written here, R A I t square. This is your equation 174. So, now question is that your what we call little bit more steady state computation will go in the next class, next lecture. So, now if you look into that T is equal to P t plus R A I t square. Now, in general if you look into this, that this part R A I t square actually very small, right. Now, if you do so, that means if you do so, that this is actually torque will be approximately equal to the power output P t, right. Therefore, in per unit system, when you convert into per unit system, if generally if you neglect the loss, you will find in per unit torque and power both are same, because this term R A I t square is very small, right. So, many in our analysis, many cases we assume it is a law, you assume that per unit torque is equal to per unit power if you convert it to this thing, because this term is very small. Therefore, torque and whatever we have made it, this torque is equal to this one P t plus R A I t square, everything is in per unit, and this term is very small compared to this term. Therefore, torque is approximately in power in per unit, right. So, only thing is that after this I mean after this we have one more thing, that is your just computational procedure, and we will take one example, little bit more derivation is there, and after that we will go for the your what you call that your dynamics, the swing equation, step by step we will follow, right, and slowly we will go into much deeper analysis, particularly in that your Laplace domain, and we will derive all this your mathematical model, block diagram representation, and later we will see that stabilizer, power system stabilizer, your lead lag stabilizer we will consider, and slowly eigenvalue analysis and participation factor, all these things will your what you call will examine, but that is in slowly we move into that. But after this we will go little bit of computational analysis, and then we will come to the swing equation. Thank you very much, we will be back.